So today we are talking about how to determine how concentrated a solution actually is. So what I mean by that is I'm saying that every time that we make a solution in class, there is a calculation that's done by myself or Miss E when we're making solutions for lab as to how much stuff we add into a given amount of water to make a solution. We call that concentration. So, like, to give a real world example, if you make the lemonade, right, with the frozen lemonade that comes out of the freezer in that can, and it goes into the thing, and it tells you to use like 3 3/4 cans of water, and you put too much water in, you've made awful lemonade, right? You've changed the concentration of the lemonade by adding too much water. Does that make sense? So, concentration in chemistry is defined as the amount of dissolved solute in a particular amount of solvent. So we always are talking about how much stuff can be dissolved in a given amount of solvent in terms of concentration. Now, there are some things that affect solubility. One of them is temperature. So temperature can affect solubility, stirring can affect solubility, and crystal size can affect solubility. So in the case of temperature, if we increase the temperature, so if we increase the temperature of the system, we can increase the amount of solute that can be dissolved in the given amount of solvent. It also increases the rate at which we can dissolve something. So by increasing the temperature, we can increase how fast something dissolves. Could somebody attempt to explain why that might be the case? Let me refresh your memory. What happens to things when you add heat to them? They move faster. So if we increase the rate at which the solvent is moving, the solvent comes into contact with the solute more often, and as a result of that, it can dissolve things faster. Stirring, also known as agitation, can increase solubility. So agitation can increase solubility because it will make solvent particles move faster and increase the amount of fresh solvent coming into contact with solute. Does that make sense? Yes, no? And then crystal size can also affect solubility. So we would call this surface area. By increasing surface area, we increase the amount of area that the fresh solvent can come into contact with solute. So increasing surface area can increase solubility. by giving So by increasing the surface area, we increase solubility by giving more places of content for the solvent particles to touch the solute particles. All of these things are ways that we can increase solubility or make solubility occur more efficiently. There are other times when solubility are important to consider. So for example, when we try to dissolve gases in liquids, the pressure of the area above the liquid surface will affect the solubility. We call that Henry's law. It's really not that important for this particular part of the class. But I guess I should go back and ask the question, what is a solute versus a solvent? Because we haven't talked about that, I guess, in a while. What's the solvent? The thing that's being dissolved into, or that's doing the dissolving, right? So like water is the solvent. What is the solute? The thing that's getting dissolved. Okay, good. Now, we can express concentration of a solution by using these three terms, and we talked about these three terms in the POGL at one point or another. I'm going to start by talking about saturated and move my way back around. So saturated is the maximum amount of solute dissolved, oh my gosh, in a given amount of solvent. So if something is saturated, we say it's the maximum amount of solute dissolved in a given amount of solvent. If we say something is unsaturated, it means that less than So we say that less than the maximum amount of solute is dissolved in a given amount of solvent. And if we say something is supersaturated, supersaturated is more than the maximum amount. Dissolved in a given amount of solvent. Now, a saturated solution, if we were to look at a solution that was saturated, you would visibly see a clear solution. Okay? If you were to look at an unsaturated solution, you would also see a clear solution. If you were to look at a supersaturated solution, you would also see a clear solution. The major difference, though, is that in a saturated solution, there might be some solid sitting at the bottom. Okay, so there might be some solid sitting at the bottom. Now, the saturated and the unsaturated are pretty easy to understand. I'm going to show you a couple of video clips of what a supersaturated solution might look like. So that would look like this. The issue is that it's water soluble, so if you pour enough of it down the drain, it will just go and eventually dissolve and go to your water treatment facility. Okay? Now, there are mathematical ways for us to express concentration. One of them is something that we call the molarity formula, which is moles of solute divided by liters of solution made. And the molality formula is the other one, which is number of moles of solute dissolved in kilograms of solvent. They both are telling you the similar ideas. In that case, how much stuff is dissolved in a given amount of water. The major thing that I want you to have a focus on here is molarity is a capital M, whereas molality is a lowercase m. So when you do calculations with these two ways to determine concentration, you have to be cognizant or aware of which one you're solving for. Yes, you should probably memorize these two formulas. So let me show you how it works. In the case of the first one, remember that it says what is the molarity, and I know that molarity is capital M, which is number of moles divided by liters. That's its formula. So in this case, it's asking me to determine the molarity of a solution made by dissolving 25.2 grams of sodium hydroxide in enough water to make 750 milliliters of solution. The issue is that I don't have either of the units, so I have to go ahead and find them. So the first thing I'm going to do is I'm going to take the 25.2 grams of sodium hydroxide and change it to moles. So in 1 mole of NaOH, I have, let's see, there's 16 plus 1.01 plus 22.99, which will give me a value of 40 grams of NaOH. So if I take 25.2 divided by 40, I get roughly 0.630 moles of NaOH. The other thing I have to do is change my volume. So I have 750 milliliters, and I'm going to change that to liters. 1 liter is equal to 1,000 milliliters, and that will be equal to 0.750 liters of solution. So when I go to solve for molarity, molarity is equal to number of moles per liter. So when I plug those values in, 0.630 moles of NaOH divided by 0.750 liters. I'm going to plug that in my calculator, so it's 0.630 divided by 0.750. I get a value here for molarity to be 0.840 molar NaOH. Now, one thing I would like to point out is that technically the unit for molarity is moles per liter. That really means that the unit is moles over 1 liter. So whenever we do a calculation, we say something is 0.084 molar or has a molarity of 0.84, that's really moles dissolved in 1 liter. Now, the next problem is asking us to determine the mass that must be mixed with 1.50 grams of water to make a 0.150 lowercase m. So that tells me that's molal. So if I know that I'm using the molal formula, molality is equal to number of moles, but this time it's in kilograms of water in this example. So the first thing I need to do is I need to understand, or I need to convert my grams of water into kilograms of water. So I'm going to take the 150 grams of water, and I'm going to convert it to kilograms of water. So in 1 kilogram, there are 1,000 grams. So that tells me I have 0.150 kilograms of water in this case. I'm looking for moles because I'm trying to find mass eventually. So when I go ahead and plug in what I know, I'm going to take the 0.150 molal will equal number of moles over 0.150 kilograms. So in this case, I'm going to take the 0.150 times 0.150, and that's going to give me, let's see, that's going to give me 0.0225 moles. In this case of glucose, C6H12O6. So if I need to figure out the mass of glucose, I'm going to take the 0.0225 moles of C6H12O6, and I'm going to convert it to grams. So in 1 mole of C6H12O6, let's see, there's 16 times 6 plus, let's see, 12 times 12.01 plus, not cosine, 6 times 12.0, oh wait, I did that wrong. Hang on, I gotta back up here. Okay, so we had 6 times 12.01 plus 1.01 times 12 plus 6 times 16, which gives me a molar mass of 192.3. So I have a molar mass here of 192.30 grams of C6H12O6. So when I plug that into the calculator, that's 192. So I'm going to take that times 0.0225. I get a value here to be 4.33 grams of C6H12O6. So any questions about using molality versus molarity? So far, so good? All right, the next thing we need to discuss is dilution. Dilution is the process of decreasing the concentration of a solution by increasing the amounts of water. So what's occurring here in this particular picture is that we have an original solution that we refer to the stock solution, the one all the way to the left, that has a very specific concentration. And if we take a sample of that and put it in the next container, and then we dilute it to the same volume, we decrease the concentration of the original solution to potentially like at 80%. And if we take a sample of the original solution, a little larger sample of the original solution, or a little smaller sample of the original solution rather, and then dilute it to the same volume, we get a slightly less concentrated solution. And we continue that down until we get almost nothing, I guess. So dilution is a process by which you take a sample and you add more water to it and it becomes less concentrated. Now, the way that we express that mathematically is the equation C1V1 equals C2V2, where C1 is the concentration of solution originally, and V1 is the volume of that original solution that's used in the dilution. C2 is the concentration of the solution after dilution, so that's what you're usually the desired volume or the desired concentration, and the total volume of the diluted solution is V2, so what's what you dilute it to. So when we go through a couple of problems working with this, For example, question number 1 says, what is the, or how much of the 2 molar sodium hydroxide solution should be diluted so that you have 100 milliliters of a 0.5 molar solution. So in this problem, I have C1V1 and C2V2. So this problem says how much 2 molar sodium hydroxide solution should be diluted. So that's going to be my original concentration. 2 molar sodium hydroxide should be diluted because it says how much, so I got to use that as a question mark, to make 100 milliliter, or to have 100 milliliters of a 0.500 molar sodium hydroxide solution. So in this case, I'm going to use the formula C1V1 equals C2V2. I know the original concentration is 2.00 molar. I'm trying to decide how much of that I should start with, or I should use. Now, I'm identifying the fact that my volume is in milliliters, so I'm going to change that to liters to keep things the same. So in 1 liter, there are 1,000 milliliters, which will give me 0.100 liters. So in this case, my secondary concentration that I want to make is 0.500 molar. The volume that I want to actually produce is 0.100 liters, or 0.1 liters. And so I'm going to go ahead and solve for V1, and that will give me a value of, let's see, 0.5 times 0.1 divided by 2 will give me 0.0250 liters, or which is roughly 25.0 milliliters. So what this problem is telling me is that if I take 25 milliliters of concentrated 2 molar sodium hydroxide and I want to make 0.5 molar solution of it at 100 milliliters, that's the ratio that I have to have. And then lastly for today, 100 milliliters of water is being added to 500 milliliters of a 0.1 molar solution. What is the new concentration of the HBr solution? Again, it's going to be C1V1 equals C2V2. And it says 100 milliliters is added to 500 milliliters of a 0.1 molar solution. So my original concentration is 0.100 molar HBr. And I'm starting with 500 milliliters of it, and I'm trying to determine the concentration after I add 100 milliliters. So I have to remember that adding 100 milliliters is going to be 500 milliliters plus 100 milliliters to give me 600 milliliters. So my final solution is going to have a volume of 600 milliliters, so I have to be aware of that. Well, I'm going to change that to liters right away. And I'm going to change my 500 milliliters to liters right away. And then I'm going to set up my formula, which is C1V1 equals C2V2. And I'm going to take the 0.100 molar HBr times the 0.500 liters, which will give me my new concentration at 0.600 liters. So 0.1 times 0.5 divided by 0.6 will give me a concentration of my new solution to be 0.0833 molar HBr, which will equal C2. And hopefully that would make some sense, because I added water to something. By adding water, I should be decreasing the concentration. Like I said, hopefully that should make some sense. So